This is our final presentation for Mechanical Engineering Design, Professor Hashemi. Our project was a motorized collapsible bike. So why would someone be interested in a motorized folding bike? Well, right now, the current products on the market are too heavy. They have insufficient motors. They don't get enough power. They are way too big, and they're not portable. They don't fold in on themselves to lend themselves to being placed in small, compact areas that you might find on, say, public transportation. So we want to make a bike that meets the needs of the average commuter who's interested in being able to fit their bike into small spaces and also interested in saving time on their commute and saving money on gas. So currently, some of the problems with non-folding bikes, well, bikes are great, but they're easy to steal, as you see around Northeastern all the time. They're not very compact, they have a big footprint, and they're sometimes ineffective over long distances. So our goal is to make bikes more affordable and more compact. A lot of times bikes, you can't fit them into some convenient place like a backpack. Oftentimes, even if you can fit them or fold them at all, they're not motorized, they're expensive, and they just don't look good.
So these are some initial sketches of our solution to all of these problems. On the right, you'll find an overall general sketch from our initial brainstorming phase of this project, which outlines where the telescoping members we imagined could be, as well as the location for the latch, which would allow it to fold into an even more compact profile. To the left, you'll see a bit more of a detailed outline of where we expected our components to go, highlighted in each different colors for each one. So we have our pins that are red, the telescoping bars, which were highlighted in dark blue, our folding wheels, which are colored in light blue, and the gearbox, which has been boxed, as you can see there. So starting out with an outline of our frame, basically the function of the frame would be able to hold all of the components in place as you would expect a standard bike frame to. The differences with this are that it would be able to fold and telescope on itself, which would minimize the stowage profile of the bike. The segments in compression would be solid and would fold in at a hinge, whereas the segments that are in tension would be the telescoping members that would basically telescope in on themselves. The design specs we went with this, we wanted it to be able to support a standard sized adult. So we went with around 250 pound maximum load with a collapsing size to be able to fit into 64-liter backpack. We wanted it to be able to fold very quickly, and the maximum speed we wanted was around 45 miles per hour when you pedal with the motor assist. And the materials we found, given these design specs and our calculations, we decided on aluminum 6061 because it's lightweight, it is cheap to use, and it would be strong enough to meet these needs. Next, with our telescoping members, these again would function to basically be able to telescope in on itself and compact into a small profile. Each member of the telescope would basically be a conically flared hollow cylinder that can nest inside itself, and the pins would be used to basically prevent any rotational motion at each joint. For the design specs for this, we wanted it to be able to withstand a maximum failure load of around 124 to 290 megapascals. And to do this, we needed a sufficient strength to weight ratio so that the bike would be able to, as well as this, a overall weight of the bike of less than 40 pounds. So the material, once again, we chose was 6061 based on these design specs and our calculations. And the user experience, in order for this to function in real life, would be a single twist pin that would collapse each member. Finally, we have the hinge members. The function of this, again, would be to collapse the entire bike, as highlighted in the circles in the picture, as you can see. Once again, the design spec here would be able to withstand a maximum failure force of 124 to 290 megapascals. And once again, we chose 6061 aluminum alloy to to maintain the design specs we chose and based on our calculations. And this would be a single latch that would release the hinge.
So we decided that it wasn't enough just to be able to fold the frame. We also decided that to really collapse the bike into a backpack, you'd have to fold the wheels as well. So we designed this custom folding wheel, which collapses to reduce the post-folded size of the bike. The materials for this, the spokes that you can see in the top picture, are made of 6061 aluminum alloy in continuity with the rest of the bike. But the smaller aspects in the wheel have to be made of 1020 HR steel to be strong enough and to have an infinite fatigue life, as they'll be undergoing a lot of cyclic loading. Like the other members, a single latch is used to release the entire wheel, and then the user can fold it like a fan with very minimum force. Next slide. For the connection design, we looked at clamps on the seat and the handlebar, which allow users to modify the height of their bike and have a little bit of customization ability. For the seat clamp connection, we assumed a force of 500 pounds because there'll be a little bit of impulsive force when someone sits down on the bike, and to factor into our factor of safety. And we chose aluminum for that because it's a very standard material in the bike industry, also 6061, and it fits in well with our design constraints. So the clamp is just a screw in there, as you can see in the middle picture, that then a user can really easily screw in and latch, and their bike seat will not fall in. We also assumed a maximum force of 100 pounds for the handlebar, although that's more than there would actually be. It'd likely be even less than that. And we also looked at 6061 aluminum there.
Okay. For our powertrain, we wanted to have a capability of a 2 meters per second acceleration, and that would get a total of a 25 kilometers per hour maximum speed in order to meet the requirements for usability for the customers. The motor and gear tray would have a size of 11 by 6 centimeters in order to be small enough to fit inside of a folding bike. For our gear train, we're planning on having a set of 2 planetary gearboxes in series. Each set of gears would have a 6.24 ratio, and as well as the ratio from sprocket the gearbox attaches to on the pedals to the sprocket on the wheels has a 2.15 ratio for a total of an 83.85 or 84 gear ratio between the motor and the wheels in order to get enough torque for our acceleration. Here's a selection of the motors and gears that we were looking at for our gear train, as well as we've done ACMA calculations on these gears, and the stress is much less than the strength of the steel that Mastercar uses for their gears. So summary of all the improvements we've made. The bike will be small enough to fold into a large backpack, so have much more kind of practical portability than a lot of other bikes. It's a relatively high power motor for acceleration and top speed. It will take at most 2 minutes to collapse. There are quite a few actual folding mechanisms, and with our single twist pin, they'll be simple and quick to put away. We also believe there'll be a reasonable cost of under $1,000 for a full production version of this bike. In conclusion, working on this bike, we've learned a lot doing it, and it's been a very engaging and challenging experience, but also we've had a lot of fun. And so if we were to take this to the next steps, that would be finalizing the design and then looking at manufacturers for all of the parts we designed.